Okay, so today I'm going to talk about the black box functor. So last time I was in charge, I started talking about it, and the idea is that it describes the behavior, by which I mean the external behavior of an electrical circuit given the circuit. So you're given a circuit and you put a black box around it, metaphorically, and all you have access to are these terminals, these ends of wires coming out, and what you have access to about them are the potentials, the electrostatic potential at each terminal, and also the current at each terminal. Current and potential are both real numbers. When we talk about current, we mean the current flowing into the inputs and flowing out of the outputs. There may be arrows on the edges, there will be arrows on the edges of our graph, but so there's a subtlety there, but like if the arrow is pointing up and the current is 5, then we think of the current flowing this way as -5. So there's some minus signs you have to worry about, which will come back and haunt us later. So Brendan proved that there's this black box functor, and I'm not going to even try to prove it's a functor because that's actually quite a long thing, but I want to at least tell you what the functor is. So right, to be a functor, to prove something's a functor, you have to prove it sends objects to objects, morphisms to morphisms, and preserves composition. So I'm not going to prove the preserving composition part, which is the key thing you got to check. But I will define the functor. So, but first I have to remind you of what the categories are. Well, so we've got this black box functor. I'm going to get sick of writing a large black box, I see. So we've got this black box functor from circuits, from rescirc. That's a category where the morphisms are circuits made of resistors, to a category linrel. That's a category where you have linear relations between vector spaces. So let me tell you how this works. So remember, just to set up notation, what these guys are. So rescirc, the objects are finite sets. So you think of an object in rescirc as a finite set of dots, which will become the dots in the previous picture, and then a morphism from some finite set x to some finite set y, I'm just changing my notation here slightly on purpose, is an electrical circuit. So it's a circuit made of resistors, but mathematically what it is it's a cospan. It's a cospan in a certain category. It's a cospan in the category of graphs where the edges of the graphs are labeled by numbers called resistances. So I talked to you about these categories of labeled graphs, and here the edges are labeled by numbers greater than 0 and less than infinity, so they'd be 0, infinity labeled graphs. So a bit more specifically, gamma, I'm just trying to remind you of all the notation. You're supposed to know this stuff, but you probably figured all my favorite letters for everything. So gamma consists of a set n of nodes or vertices. Well, you have to use the letter n instead of v because we've also got voltage running around. Once upon a time, this was called I, and that was called O for input and output. But now we're going to have current running around. And a sacred tradition in electrical engineering is that current is denoted by the letter I. $5 if you can tell me why. And so we run into a conflict between currents and inputs. So inputs are now X. So a set N of nodes, a set E of edges. Fine terms. We have source and target maps. It tells you where each edge starts and ends. So S and T going from edges to nodes. And then finally the labeling. Each edge gets labeled with a resistance, which is a number from 0 to infinity. Okay, so that's gamma. But then this is X and Y are also such entities. They're also labeled graphs. But they're sort of silly ones because they're just finite sets masquerading as labeled graphs. So the idea is if you have any finite set, you can make up a graph where that set is the set of nodes and no edges at all. So for these two guys, X and Y down here, the set of edges is the empty set, and that means you don't have to worry at all about what these source and target maps or resistances are. They're just the only thing they could be. So I described to you what a morphism between labeled graphs is, and so that's what we've got here. But the picture you should have in mind is you've got this set X here, this set Y down here, and then the labeled graph itself, which could be sort of anything. Maybe I won't bother drawing the numbers, which are all the resistances. So imagine some numbers on these wires. But you'll notice that the nodes of this graph, they're not literally the same as the elements of this set X and this set Y. There's a map. I forgot to name these maps. There's maps, input and output maps, I and O, mapping those graphs, X and Y, to this graph gamma. So each of these dots up here is getting mapped to a dot in gamma, and similarly down below. And in the simplest cases, the cases that seem sort of the most obvious to understand, that map really just includes X as a subset of the nodes of gamma and includes Y as a subset of the nodes of gamma. And so in that case, you can just sort of clean up your picture a little bit and just draw it like that. Just think of X as a subset of the nodes of gamma, similarly for Y. But I didn't say that I and O are one-to-one, so they might not be. And I also didn't say that the range of I, or the image of I, is disjoint from the image of O. So you could even have cases where the same node was in both the image of an input and an output. Those cases are a little bit scarier to think about, but they're very important. But I don't want to think about them too much right now. So just to get going, you can imagine a picture like this. So X, anyway, is the set. We'll always call that the set of inputs. Y is the set of outputs. And then we're very often interested in taking the image of the map I, union the image of the map O, and get some subset of nodes, which we'll call T. Sorry, T is defined to equal this, which is a subset of the nodes. So these will be called the terminals. So in the nice cases, like the one I've drawn, the terminals can be viewed as just a subset of, well, the terminals always are a subset of the nodes, but in the nice cases, the set of terminals is isomorphic to the disjoint union of X and Y. But in the non-nice cases, that may not be true because MI and MO may not be disjoint, and I and O may not be one-to-one. maybe I should draw you one weird case just so you see what's going on. For example, here's an example. Here's a very important example. There it is, okay? So that thing there is gamma. In this particular case, gamma is a graph with just one vertex and no edges. And x is a thing with just one vertex and no edges, and it's getting mapped into it in the only way it can, and similarly for y. So that's a degenerate example. That's not a circuit that you typically buy in a Circuit City. If they sold these, they'd gone broke even faster than they did. So this thing would, well, what would this thing look like if you built it? What would it be? Oh, come on, use your imagination. Yeah?
It's a plain old wire.
A plain old infinitely conductive wire, or the way I'm drawing it, it's not even an edge, so it's just like a little blob of copper is the way I think of it. Just like a little tip of a wire, like a little conductive ball, right? So this is a very important circuit for mathematicians and not for electrical engineers, because this will be an example of an identity morphism. This kind of, if you take one of this kind of circuit and you glue it onto some other circuit, you don't even notice that you've done anything. You're just taking like this little piece of copper and stuck it on the end of your wire, and so that's good. That's an identity morphism, right? An identity morphism is a kind of function that only the mathematician could love, because it doesn't do anything, but for some reason it's great to have it. Why? Let me figure out why identity morphisms are so good. So this is an example here. Or, well, while I'm at it, having so much fun, you can do an example like this, where gamma looks just the same as it did before, is exactly the same. X could consist of 2 points. So they both have to be mapped to the same point here. And you could have y be various things, but one thing you could have y be is the empty set. There's no law against the empty set. So this is in the funny circuit that has 2 inputs, no output, and 1 terminal. And can anyone say, well, it would look just the same as this, okay? But it would be, do something different with it, because you'd be hooking 2 inputs up to this copper dot instead of just 1. Can anyone say why this is a good thing? Jason mustn't know why it's a good thing. No, he doesn't want to say. Okay, well, you don't want to say. So Jason said that this thing reminded him of like a purely conductive piece of wire, which is true. Although we don't want to think of it as an edge, because it's not. So what does this thing look like in the same scheme?
A U-shaped wire.
Yeah, a bent wire, a wire like this. So that's an important circuit component. If you look at a complicated circuit, like underneath your television set with all those wires twisting around, you'll see lots of little portions of it that look just like that, like a bent wire. It's not so important by itself, but it's something that's part of some bigger messes. So these kind of circuits turn out to be very important. This is going to give you identities, and this is going to be crucial for making our category into what's called a compact category. A compact category is where you can take a morphism, and you can take its output, you can go bend it around to make it be another input, which you can do in lots of categories, like the category of vector spaces, for example. So anyway, so those are the weird examples, and I guess I just had to mention them because I saw people staring at this and going, what is he saying? And the more I said, don't think about it, the more you guys are going, okay. So, very well. So that's a morphism in ResCirc. I don't think I'll even say much about how we compose them, although I said a lot about it earlier. We compose them by, and Francisca said more about this type of thing, we compose them by doing push-out. It's a way of composing cospans. Actually, really, I'm working with isomorphism classes of cospans here. That's not very long. Okay, then LinRel is much simpler. So the objects are finite dimensional vector spaces, finite dimensional real vector spaces. And the morphisms are not linear maps between these, but they're something a little bit more general. They're linear relations between these. So a morphism from some vector space U, some vector space V, is a linear relation. So a linear relation is just a linear subspace of the product of U and V. If you like to show off your math training, you can write it a direct sum. Same. So the idea is that certain vectors here are related to certain vectors here, and the ones that are form a subspace. Thus, it's a linear relation. It gets along with addition. Okay, and we compose relations in the way that I described once before. Basically, if I'm related to you and you're related to someone else, then I'm related to that someone else by the composite of those two relations. Okie doke. So now I want to get into the meat of things, which is to define this black box functor. So to tell you what it is, I got to tell you what it does to objects and what it does to morphisms. So on objects, it's very simple. So the black box functor will take some finite set and give you a vector space, and the vector space that it will give you is just r to the x times r to the x. Two copies of r to the x. So sort of the most famous way to turn a set into a vector space is to do this thing, r to the x. But we're doubling it here because there's a really fundamental fact about electrical circuits, which is that there is electrostatic potential and current, both of which play key roles. And so this vector space is just big enough to tell us, a point in here will tell us what's the potential and current at each of the points in this set X. So X, you could think of as like a set of inputs or a set of outputs, and you want to know when you're playing with circuits what's the potential at each point and also what's the current at each point. So a pair IV in r to the x times r to the x describes, whoops, I want to do potential first, and I want to call it phi. So this pair here will describe the potential phi sub x and current I sub x at each point in there, point x. Okay, that's nice. So then, what's going to take the rest of the time, unless I manage to go rapidly, is what does this functor do on morphisms? That's the meat of the whole subject. So we're supposed to get a linear relation from each actual circuit. So what we need is, so we're given some circuit with x as inputs and y as outputs. Given that, what we need is a linear relation. This is a rather longish name for a morphism, so I don't really want to write parentheses and then put this big fat diagram in there. I could. Yeah, what the heck. I will. But often I will just get lazy and abbreviate this mess as just gamma. It's just like an abbreviation.